Okay, well, welcome to my talk, Competing with Bruce in the Nerdiest Competition Ever. I'm Paul Dyson. I'll say more about me later, but I'll just get into the talk. Warning, there is some maths in this talk. I was warned not to put too much maths in, but there is a bit at the start. But don't worry if you don't follow along with all the maths or you don't find that interesting. It doesn't affect the main thrust of the talk, the main story of the talk. And this talk does concern prime numbers, so I'll just give you a refresher on prime numbers. You can tune out if you're not that interested in maths. But prime numbers are numbers that can't be evenly divided by anything except themselves and 1. So the first few prime numbers, 2, 3, 5, 7, 11, 13. For example, 7 is a prime number because it's got no factors except itself and 1. 1 times 7 is 7. But 6 is not a prime number because it has 2 factors. 2 times 3 is 6. 6 can be a rectangle, whereas 7 can only be made into a line. And in this talk, I'm interested in primes, numbers that can only be in a line like that don't have any factors. What's the point of prime numbers? Currently, they're very useful because they're used in encryption. So you're using prime numbers when banks are doing transactions. If you're doing secure messaging, you're using prime numbers. And most web pages now are HTTPS, which once again uses prime numbers behind the scenes as part of the encryption, using the fact that if you take 2 large prime numbers and multiply them together, if I give you the answer, it's very hard to work out what the 2 prime numbers were. But to get more onto what I want to talk about in this talk, how would you find the next prime number? If I give you a number and say, what's the next prime number that comes after this number? And the thing is, there's no simple formula to do this. You have to do some sort of computational procedure. There's a few different things you can do if you want to find the next prime number. One thing is trial division. You want to see if this number can be divided by anything. So you can just try dividing it by all the numbers less than it and see if it is. Take your number, divide it by 2. Does it work? By 3, by 4? And if it's not divisible by any of these things, then it's a prime number. You can do this a little bit more efficiently because it turns out you only need to divide by all the prime numbers up to the square root. But anyway, this is one sort of method of finding prime numbers, and it's got one version and a faster version. There's other ways that you can find prime numbers if you wanted to. Another way is using a sieve. So for example, if we wanted to find all the prime numbers up to 100, then you can have all the prime numbers here. 1 isn't a prime number, so we leave that off. And for the sieve, you start, what's the first number that's in the sieve? It's 2. So you say, oh, 2 is a prime number, but now let's get rid of everything that's a multiple of 2. Let's cross all of those off. They can't be prime numbers because they're all divisible by 2. And then we just keep doing this procedure. What's the next thing in the sieve? Oh, it's a 3. Well, let's get rid of all the multiples of 3. And we get rid of all of the ones that were left that were multiples of 3. I've got rid of in the green there. The next number is 5, so that's a prime number. We get rid of multiples of 5. And the next number is 7. We get rid of multiples of 7. And it turns out that's all you need to do to find all the prime numbers up to 100. So this is a far more efficient method. It doesn't involve any division, which is slow computationally. It just involves crossing off numbers. So this way of finding prime numbers is actually behind the calculations that I'll be talking about, but you don't really need to know. If that was too quick to follow and you're not interested, it doesn't matter. But that's one way of finding prime numbers. And there are some numbers that are special numbers where there are faster methods to finding if they're a prime number. But the point is there's no simple formula. Right? All of these take some sort of time. You need to do some sort of compute to find the next one. And along those lines, I'll just read this so I get the facts correct. Hello? Okay, I'm back. For 30 years, the great internet Mersenne prime search called GIMPS has been searching for the largest prime numbers. Thousands of volunteers around the world run code on their CPUs, each doing a small piece of the search. And by 2023, GIMPS had found the largest prime 17 times. each time beating the previous record. But it hadn't found one since 2018. For 5 years, it hadn't found the next one. Everyone been searching on their CPUs. So along came Luke Durant, a former employee of GPU maker NVIDIA, and he said, people are not treating this as a race. People are too complacent. They're just letting their PCs, their CPUs chug along. We need to take this seriously. This is a race. We need to find the next number quickly. So he set up a GPU framework. He used thousands of server GPUs, 24 data center regions, 17 countries all over the world. And he used his own money to pay for this. And when asked, he said, well, it was less than $2 million. So, well, that's good. He had a spare $2 million to spend on that. And by October the 12th last year, he had found the largest prime number. I mean, in conjunction with GIMPs, like they were all together, but he was a gigantic part of it and everyone else was a tiny part of it. And he found the number that's there, 2 to the power of 136 million, minus 1. So now we come on to me and this talk and what I've been doing the last few years. I was at Google from 2011 to 2024, but this talk's not about that. This is about something I did outside of that time, being a prime sequence searcher from 2020. So this talk, like Durant, it will involve primes. It does involve a race. It'll get into GPUs at some point. It involves lots of machines. Well, if lots is maybe a dozen or more, mainly in my home. And whereas the other one was, well, less than $2 million, I probably spent less than $2,000 a year on this project. So this begins with the Online Encyclopedia of Integer Sequences, the OEIS. This is where your name gets recorded if you find the next number in a sequence, like the largest prime. And I wanted to get in there. I wanted that to be my claim to fame. I want to find a number, part of a sequence that nobody has found before. The problem is that all the easy and not so easy numbers to find have already been calculated by someone, right? There's thousands of sequences in there. Many are hard to understand. So where should I begin? I mean, in there are very normal sequences, everyday sequences, like the positive integers, right? That's a very basic sequence. The prime numbers are in there as a sequence. Things like powers of 16. But they're not things where you could maybe find a new number, powers of 16 or positive integers. But there are sequences where the next number is not known and you could find it and get in there. For example, the Fermat primes, that would be very hard to find the next one. It's probably gigantic. And then there's all these esoteric things that who knows what they are, right? Number of ways of placing 2n-1 non-attacking queens on a hexagonal board with edge length n in Glinsky's hexagonal chess, whatever, right? Like, I don't know what any of that is, but maybe if I worked it out and I worked out an algorithm, maybe I could find the next number, right? But where do you begin? Which sequence? So during COVID, a YouTube channel that I like watching, Stand Up Maths by Matt Parker, he was setting puzzles for high school students during COVID. And he set a puzzle, when is the sum of the squares of the first n primes divisible by n? And it's true for 19. When's the next time it's true? Now, this is the thing I ended up looking at. So I'm going to go through this in a bit of detail. If you're not into maths, maybe just tune out for a bit. But I'm just going to go through this. When is the sum of the squares of the first n primes divisible by n? So let's just think about the first 2 primes, right? This is the sort of thing that I'm looking at. When is the sum of the squares of the first 2 primes divisible by 2? So we're going to have 2 numbers. The first 2 primes are 2 and 3. We want to square them. So we've got 4 and 9. We want to add them up. 4 plus 9 is 13. And we want to see if this is divisible by however many there were. There were 2 of them. So is this divisible by 2? And it's not, right? It's 6.5. It doesn't go evenly. We want this to be a whole number solution. And just to write the equation all together, it might be easier to picture, right? The sum of the squares, 2 squared plus 3 squared, and we're going to divide it by 2. But it doesn't go evenly, so that's not in the sequence. That's not something we're looking for. Whereas, as Matt Parker said, 19 is a solution. So if you look at the first 19 primes, and then you square them, and then you want to add all of those up, you get 24,966. and you want to divide it by 19, and this goes evenly. So this is a number in the sequence. And, oh, hang on, there's the whole equation again. It might be a bit easier to picture it that way. And as I said, it divides easily, so it's in the sequence. Now, when Matt Parker released that video, you might think that this would be a fairly common thing to happen. But actually, when he released the video, there's only 12 known solutions. And they get pretty big pretty quickly. I mean, he'd said that 19 is a solution, and he was challenging high school students to find the next one, which is 37, which you can pretty easily do in like Excel spreadsheet or even on a calculator, perhaps. But when it was released, there's only like 12 there. And the biggest one is 51 billion. That's not that large for a computer. And like, oh, well, if I want to get in the OEIS, maybe I can find the next one, right? I could calculate that. But that's when the video was released. I didn't actually see the video for a week later. A week later, these solutions were also in the OEIS because a lot of people had exactly the same thought that I had. Oh, that's an interesting sequence. Let's see if I can find the next term. So a week later, instead of having to get bigger than 51 billion, I would have had to get bigger than 51 trillion. And now it's like, oh, okay, maybe that's going to take a while. Maybe that's a bit tricky. Looks like I've missed my chance. Maybe I should try and find some other sequence. But this is the sum of the squares of the first n primes. What about the sum of the cubes of the first n primes? It turns out that's in the OEIS. And so is the sum of the fourth powers, fifth powers, even the sum of the 19th powers, that's in the OEIS. Maybe I could find the next term there. And even the most simple one at the top there, just the sum of the first n primes. That's a nice sort of pure idea, pure sequence. Just add up n primes. Is it divisible by n? So I looked in the OEIS, and I'm doing this in December 2020. And the sum had been recently updated in January 2020. It was up in the trillions. The sum of the squares, as we just said, has been updated. But the other ones, people had thought to do the squares, but no one else had thought, what about the cubes? What about the fourth powers? What about the fifth powers? I think I can get in with these because they haven't been updated since 2013. That's 7 years ago. And the numbers are only in the billions, or the fourth power, it's only in the millions, 2007. Okay. So let's go. So brute force, try every value in turn on the computer, see if we can get an answer here. And after a few hours, I found the sixth term for the 16th power. Never been found before, wasn't known to man, wasn't known to humankind. Thank you. Thank you. So that's the beginning of it. And I was pretty happy because there was only 5 terms known, and I'd found the sixth one, and it was a lot bigger than any of the others. Okay, so that's success. So here I am. I put it in the OEIS, December 30, 2020. I'm doing this in the holidays here. And I get in the OEIS. But I mean, if I just put one in, what about all the others? Surely I can get the record for all the other numbers as well. So I start running it on every computer that I can find in the house, old ones and laptops and things. And just as to how I'm doing this, there's a program prime sieve in C that's very fast at factoring primes. And I'm using the GMP large integer library to handle large calculations. So in the next week, I found and put in the OEIS the biggest numbers for the 5th, 8th, 7th, 14th, 11th, 3rd, 18th, and 6th. 6 powers of these sequences. And I've got this diagram here on the side where green shows you all the ones that I've put in. I've got the record for those ones from 1 to 19. So that's just in one week, right? So basically the trick here is finding things that nobody's looked at for 7 years. But anyway, so these are in here. And then now let's get them all, right? Let's get all the ones from 3 to 19. 1 and 2 are a bit big, but let's go 3 to 19. So in the next 2 weeks, I keep running these computers. And so I was looking up to about 2 trillion, and now I'm looking up to 5 trillion, 5 trillionth prime number. And so now I've found these other ones, the 4th, 10th, 12th, 13th, 15th, 17th powers. So now I've got everything from 3 to 19, except the 9th power. And it's now the middle of January, holidays are over, I'm back to work, things to do. So I don't have time to actually put all these in the OEIS. I'll just keep the 9th power running. It'll probably finish soon. When that finishes, I'll just put them all in. So it actually took 2 months. So this laptop sitting in the corner running for 2 months, eventually found the next solution to the 9th power. And it was like 10 times bigger than the other solutions, right? It's 50 trillion. So I put the 9th power in the OEIS, I've got it in, and now I've just got to put all these other ones in that I found 2 months ago. But someone else had already put them in. In the 2 months I waited between when I'd found them and when I then went to put them in, someone else found it, had the same idea as me. Look at all the other numbers. So I was beaten by Bruce G. I was going to name him, but I found out then this is getting recorded. So Bruce somebody found all these other ones, right? So I emailed Bruce and I found out that he was better at optimizing the code than me. He was running all the powers from 1 to 19 on these computers he's got. I did find a faster algorithm for just doing the sum, the first power, which avoided all multiplication and division. But it didn't work for any of the other higher powers. So I could never catch him. He was ahead of me. His code was faster. He was running them all. So I couldn't catch him unless something changed. So I just bided my time. For the rest of 2021, Bruce beat my solutions for three times, 5, 6, 7, 8, 11, 16, and 18. So by the end of 2021, the only one I had the records for was 9 and 14. So a year on, it's Christmas, New Year's break again. Time to play with this again. My daughter was working during the day over that break, so I borrowed her computer that had a GPU, and I ported the code to the GPU. And that was much faster. So on the 4th of January, 2022, I bought a desktop with a medium range sort of GPU. And to do this, I found code CUDA Civ that did the prime numbers on the GPU, and I had to customize the GMP large integer library for the GPU to get it to work for the things I wanted. So, okay, now I'm going to get stuff back from Bruce. I'm going to do the third power, and I'm going to run it on my GPU much faster, and I'm going to get this back. And Bruce doesn't know I'm doing this, by the way. He doesn't know I've got a GPU. So on the 7th of January, I start running the third power on my GPU. 8th of January, Bruce puts a new term for the third power. I'm like, what? Oh, I'm trying to catch you, and you've just put another one in. Okay, so then on the 10th of January, he gets the 9th power off me. So now all I've got is the 14th power. Okay, so he didn't know. And just about 6 months later or something, I was chatting to him and I mentioned I had a GPU. And he said, oh, GPU, that's interesting. I might try that in the holidays. And I've never emailed him since. I'm not pushing that at all, right? Just don't do that. Anyway, back to where I was. So he's got the 9th power. But then on the 11th of January, I find the third term, the one that he just found, right? I missed it by 3 days. If I'd started 3 days earlier, I could have had the top one. But the promising thing was that I'd found in 4 days with the GPU what had taken Bruce like a whole year to find on his CPU. So I'm definitely faster here. And a few days later, by the 14th, I've actually found the next solution bigger than his. And so then, by the 17th of January, it's in the OEIS, and I take back the third power. So, and only 9 days after he's put one in, I've now put the bigger one in. So there we go, I've got 3. Now, January, February, I start taking back terms. I've got 3, I get 5, I get 7. The odd power solutions, turns out they have more solutions, the odd powers. So I'm doing those, so I'll find solutions quicker, get more numbers in there. But after doing 3, 5, and 7, Bruce had got the first power, which I sort of like that because it's a nice pure sort of thing, just add them up, divide it. And also originally I thought it was too big to find the next one, but he's got that one. So you know, maybe I should do the first power. But I'm thinking, gee, how long is this going to take? So the third power that I got just before, it was 188 trillion, took about 7 days. The one that Bruce has just found for the first power, it's a similar order. And when you look at the numbers for the first power and sort of see how much bigger is each solution from the next one, it's about 8 times bigger. So I'm thinking, okay, it's going to be about 8 times bigger. It's going to be about 1.2 quadrillionth prime number. So if you multiply that out, it'll probably take about 60 days. So I'll stop taking back all the other numbers. I'll just spend my 60 days to get back the first power. So I started running that on the 5th of March, 2022. And that wasn't all I was running. It turns out there's another related sequence that's in the OEIS that I could check at the same time. So what I had been doing, if you remember, is adding up the first n primes and then dividing by n. A different thing you can do is add up the first group of primes and divide by the last prime. So for the example, if the first 2 primes are 2 and 3, So if you do 2 plus 3 and then you divide it by 3, you divide it by the last prime, and you see if the last prime evenly divides it. And so 2 plus 3 divided by 3 doesn't work. That's not a solution. But 2 plus 3 plus 5 is divisible by the last prime. So that is a solution. And the only known solutions for this one, there was only 5 known solutions, and no solution had been found in the 21st century. It was quite a while ago that anyone had found a new one for this. So I started my search by doing both of these things, right? Take the sum, divide it by n, but also take the sum divided by the last prime. And after 41 days, I found a solution for this other type that I was talking about, where you divide it by the last prime. And it was a 1.4 quadrillionth or so prime number, around 55 quadrillion. I've got it there. But this is one of the ones I'm most proud of because it was such a big number. Actually, I think I'll say on the next slide. Yeah, it's like only 6 values were known. And it's the first time found for that one in the 21st century. So I was very happy to find that one. Oh, thank you for the applause I was trying to get. Thank you. Now, so I've been going 6 weeks, but I still haven't found the other solution, right? The one where you divide by n. So I keep running it. But while I'm running this, Bruce is taking back the other numbers, right? So I'm running this, and then March, he gets 14 back from me. I get a bit thick. I'm thinking, oh no, he's going to be taking them off me. So I'll stop doing the first power. Let's get 9. I've got 3, 5, 7. Let's get 9. So I switch back to the 9th power. But while I'm running it, Bruce gets 3 back. Then 11th of August, I finally get 9 back. So then I switch back to doing the sum, the first power. September, Bruce gets 7 back. By the way, this competition and stuff, I think it's only in my head. Like, I don't think Bruce knows any of this is going on. I think he's just running his slowly. But this is the thing that I was saying about Luke Durant, right? Treat it as a race. That's what I'm doing. This is a race, and I'm gonna win this. So in September 2022, finally at the end of September, I find a new solution. Not what I'd estimated, about 1.2 quadrillion, but 5 times bigger. 6.3 quadrillion prime number. Took 7 months of running my GPU 24 hours a day, 7 days a week, running it all the time, 7 months. So now I've got 1, 5, and 9, and the different one dividing by the prime. But I'm not competing with Bruce on that one. So then I've got all these sort of laptops that I was running before, and I thought, well, is there a way I could use them? I mean, the GPU is really fast. These are slower, but I do have quite a few of them. And these are a picture of the actual laptops that were running when I got them going, doing stuff. The problem is that this problem is a sequential problem. And so that makes it hard to run on several laptops at once. To give the example of what I mean, like let's say I have a very long ladder, 300 steps high, and I want to check it's safe. I want to stand on every step. I want to climb the ladder and stand on every step. So with one person, I could just climb on every step, and it would take a long time. But let's say I have 3 people, and me, Matthew, and Stephen. I know 2 Matthews and 1 Stephen in the audience. So maybe this is you, but maybe it's not. For legal reasons, this could not be you. Might not be you. So there's me, Matthew, and Stephen. So what I say is, look, I'll start at step 1. Matthew, you could start at step 100, and Stephen, you start at step 200. We'll all climb at the same time. And this will be like 3 times faster, right? I'll do the bottom, you do the middle, and you do the top. And then Matthew says, yeah, but how do I get to step 100? And I say, well, just climb up to step 100. And now, like, you've lost all your parallelism or anything, because they've got to get it to 100. Well, I might as well climb to 100 and done the whole thing myself. Like, if you need to do all the first 100 steps before you can start at step 100, you don't get any advantage in this way of having 3 people. And I've got the same problem with my laptops, because you could say, well, let's start the first laptop at the first prime, and the next laptop will start you at the billionth prime, and the next laptop will start you at the 2 billionth prime. Well, the problem is this is very sequential, because, like, let's say you add up the first 100 prime numbers and check it. Then the next thing you want to check is the first 101 prime numbers. So you use the sum that you did for 100 to add on the next prime. And then you've got 101, so you use that sum to get the next one. Whereas if you say to a laptop, okay, you start at the billionth prime, the first thing the laptop needs to know is, well, what's the sum of the first 1,000,000,001 primes. And it would need the first laptop's solution at the end before the second laptop can start. So the problem is this is like a sequential problem. You can't get a second laptop going really until you get the answer from the first laptop at the very end. But fortunately, there is a faster way to sum the primes than just adding all of them up. There was code already existing on the internet called prime sum, which will quickly give you the sum of a certain number of primes. So if you wanted to start at the 1,000,000th prime, you can run this thing and it'll quickly say, here's the sum of the first 1,000,000,000 primes, start your code there and start running. The problem was I needed this for powers of primes, right? Like I want to know the sum of the squares of the sum of the squares of the first 1,000,000,000 primes. Like if you square each prime and add them all up, which this code didn't do. But fortunately, the code referred to a mathematical paper, which if you find other papers by those authors and you read those and you look in all the maths, you can eventually find the logic to be able to do this. And so I was able to convert this summing code into code that would do any power. So now, if I want to start a computer somewhere, if you want to start a computer at the, where am I up to, like 1 quadrillion, at the 1 quadrillionth prime number, instead of having to add up all those quadrillion primes, or all those quadrillion primes squared or cubed, which would take weeks or months, I've now got code that maybe within an hour will say, well, here's your starting point. So by having this code, I can now run something on several computers at once, all at the same time, and get some parallelism that way. So I got more computers. I bought old, cheap desktop computers. Friends and family donated computers to me. I wrote a Dropbox client to control a friend's machine in Melbourne so I could send the primes to her and get the results back automatically. Hello, Wendy, who's on the call. And then later on, I've used free AWS and Oracle Cloud, but they're quite slow, the free ones, because they don't expect you to run 100% 24/7. You can run like 10% 24/7, which makes them a bit slower. So anyway, I've got all this running. I've got 15 different computers, all different speeds. One's a server sending out the numbers to all the other computers and over Dropbox and everything. And I've got my load balancing, so the faster machines get more numbers, and it all goes around. And by doing all of this, all of these CPU computers were about as fast as the single GPU. So I've managed to double my capacity here. It did mean my power bill was pretty high, but it does keep my apartment warm at the moment, particularly in winter. All these computers running, and I am open to more computer donations, particularly if you've got a good GPU and you don't need the computer anymore. I'd be very, very happy to have that. So 2023, by running these GPU and the 14 or 15, whatever computers, 24 hours a day, 2022, 2023, I managed to get back 6, 11, 13, 19, all that. So all the ones in green I've got back. The ones in red I still hadn't got. 2024, got back 7, 3, 15, and 4. I'm now searching to get those between 1 quadrillion and 4 quadrillion. I've searched all the numbers from 8 to 19 up to half a quadrillion, and the other ones up to 1 quadrillion, and these ones I have to search a bit more to get them. But now where we are, 2025, I still need to beat Bruce at 14 and 16. 14, I'm up to 4 quadrillion searching. 16, I'm up to 3 quadrillion. And the one that I need to get, neither Bruce nor I have ever got, the number that started this whole thing off, to square the primes and sum them up, the 2, I still haven't got that. And I'm up to 9 quadrillion in my search and still haven't found it. So this year I've improved the GPU code, made it about 30% faster so I can keep searching. And give me your old GPUs if you don't need them, if they're pretty fast. If you'd like me to talk to your group, here's my LinkedIn. Or if you want to contact me for any other reason, there's my LinkedIn. So thank you. Did anyone want to ask any questions? I haven't done that yet. No. Well, 3 to be 5. I guess some sort of quad, but 5. What is it? Quintillion. Quintillion. Yeah, I'm nowhere near quintillions. The single-digit quadrillions probably take me a year to do a few single-digit quadrillions. So, yeah. Yeah, Stephen. You Yeah, so maybe it was a different Stephen for legal reasons. I don't want to leave you up there on the ladder. Yes, yes. I've never been worried about it until now. It hadn't occurred to me. Yeah, yeah. Yeah, right. I don't really know where to publish these things. I was hoping I'd get a question on that, so I could just talk about a couple more mathematical things very quickly. One thing, there's no even solutions. For even powers, there's no solutions divisible by 3. For 12, you can look up the rules, but there is a little rule here. The kth power has no solutions divisible by prime p if p minus 1 divides k. So that rule, that got put on the OEIS by someone else. But then when I was in a pool in a resort in Fiji, I finally worked this out, which I then added to the OEIS, but I don't really know where to publish it, which is that if you find 19 is a solution to the prime squared. And it turns out it is also a solution to primes to the 20th power, primes to the 38th power. In fact, in general, primes to the 18k plus 2th power. And there's a general form there using the Carmichael function. As far as I know, no one else has found that out. But if you put that question into any LLM, it very quickly gives you the proof and says, yes, it's true, this is why. So it makes me think perhaps it's not that original. Because all the LLMs can immediately tell you that's the solution. But the nice thing about it means that if I do find a solution for 1 power, it is actually also a solution for infinitely many other power sequences of different primes. So they're my little mathematical bits. And I did put that in the OEIS. I don't really know where to publish any of this stuff, but that's what I did. He was trying to find out the largest prime known. Whereas I'm trying to find primes that obey these particular rules to do with summing and dividing by things and whatever. Yeah. Yeah, Matthew. The cost of your power bill. Do you want me to stop?
I'm going to ask that question at the break because we're running a bit behind. That's awesome that so many people are interested in this. I was like, this amazing when I the preview. So if you don't mind, I'm just going to wrap that up. But please, Paul is around. Definitely ask all the questions. Thanks again. Okay, so we're going to have a break now for, I'm just going to put 7:05 to give enough time to run to the bathroom. So if you can come back here for 7:05, we have a panel discussion led by Rob on there's still some human